is Yasutaka Ikuta from Japan Meteorological Agency. I'd like to talk about mesoscale hybrid data assimilation using tangent linear and adjoint model of 3 ice cloud microphysics. Okay. So the Japan Meteorological Agency has been operating the global NDVH system and mesoscale NDVH system and local NDVH systems. The main purpose of these NDVH systems is to provide disaster prevention information. The mesoscale mode and local forecast mode is using the cloud microphysics process. This microphysics process is 3 ice, 6 class bulk scales. The prognostic hydrometeors are water vapor, cloud, rain, ice, snow, and groupers. These hydrometeors are needed to calculate the reflectivity and cloud irradiance in the data assimilation systems. The data assimilation method to make an initial condition of mesoscale mode is 4-dimensional variational data assimilation. In these systems, hydrometeors are not control variables. So we plan to replace this system to hybrid 4D BER. And this is a hybrid 4D BER cost function. Firstly, I'd like to talk about observation term. The observation term has tangent linear mode operators here. This is a gradient of observation term. The gradient has adjoint mode operators. The tangent linear and adjoint code of cloud microphysics is needed for reflectivity and cloud irradiance direct assimilation. So especially unbiased scheme is the best for data assimilation. So we have been developed the unbiased cloud microphysics for data assimilation. The shape of ice is varied, and the size of distribution is small dispersion, and mass is proportional to square diameter. And snow size distribution is exponential plus modified gamma. It's based on mid-latitude cloud of field, and mass is proportional to square diameter, and bulk snow density is inversely proportional to diameter. This figure is the bulk snow density. The x-axis is the diameter, and y-axis is the density. It's inversely proportional to diameter. So I'd like to show the nonlinear performance of nonlinear cloud microphysics scheme. And this slide is infrared imager 10.6 micrometer. And this is observation. This is simulation brightness temperatures using original operational microphysics. So you can see the simulation brightness temperature is lower than observation brightness temperature. The next slide, this figure is using new microphysics scheme. So you can see the simulation brightness temperature is same as observations. Next, I'd like to show tangent linearization of microphysics scheme. These figures are nonlinear microphysics scheme, nonlinear microphysics. And this is nonlinear perturbation. These are tangent linear perturbations. So this line is cloud, rain, ice, snow droplets. The tangent linear is almost consistent. However, ice nucleation is a strongly nonlinear process. So you can see the snow error is originated from the difference in these ice perturbations. Next slide is the function of adjoint mode of cloud microphysics. So we prepared the shoot observation. This is a reflectivity. This is a brightness temperature. The brightness temperature is a simulation of GPM, GMI, all channels. Upper figures a first guess, and lower figures a true minus guess. The circle point is a shoot observation point. This figure is a gradient vector. The gradient vector is inputted the previous observation into the adjoint equations. So this figure is the reflectivity, and this figure from the brightness temperatures. The reflectivity observation plate doesn't have direct sensitivity of water vapor, cloud, and ice. So this figure is water vapors. The gradient of water vapor are given by rain, snow, and groper through the adjoint modes. And moreover, adjoint of solid phase process propagates the observation information to upper atmosphere. Then I'd like to next topics, the climate-risk term. And this background covariance is given by statistics of forecast error. And this slide shows the statistical background error vertical covariance. And this is given by NMC method. This figure is a correlation in July. This is correlation in January. This figure is a covariance. The red line shows the covariance in July, and the blue line in January. So you can see the hydrometeors, this area is hydrometeors. The hydrometeors covariance is dependent on the season and meteorological situation. So we need flow-dependent background error covariance. And hydrometeors has a large correlation in each other element, and vertical, this is vertical velocity. The vertical velocity has a correlation with hydrometeors. And next, I'd like to show the simplification of background error covariance. These are analysis variables, the UV, ground temperature, and surface pressure, and potential temperature, and soil moisture, and shoot, relative humidity, and hydrometeors. And we made the rank detection, so correlation between the U and V is ignored. So because of weak correlation, U and V has weak correlation in statistics. So U and V cross sum is here. It is weak correlation. And vertical velocity is ignored. And because of effect of vertical velocity is lost on early time in the forecast. And the pressure is converted to the surface pressure and temperature. The pressure is a function of surface pressure, and the temperature is described surface pressure and the temperatures. So full matrix of background error is transformed to the block diagonal matrix. So computation cost is reduced. Next, the three topics. the flow-dependent terms. This background covariance is estimated from ensemble forecast. This term measures the fit based on the flow-dependent background error in various meteorological situations. The flow-dependent term, the implementation of the flow-dependent term is based on extended control variable method. The background error covariance is mixing meteorological background error and ensemble estimated background error. So analysis variable is given by control variables and extended control variables using the weight coefficient. And ensemble estimated background error has a spatial localization. In this study, the spatial localization is static. This time propagation is ignored. So next, I'd like to show impact experiment using real observation data. We use the GPM-DPR data. So GPM-DPR has a K band precipitation radar and KU band precipitation radar. The red dots are KPR and blue dots are KUPR. So in this study, we use only the liquid phase data, and the solid phase is rejected. If solid phase is used in the solid phase data is assimilated in this system, so forecast is changed to worse. And super observations configurations average area is 15 times 15 square kilometer, and vertical distribution observation is thinning. The vertical interval 500 meters. The spaceborne radar observation operator for GPM-DPR it's so simple. It's simple because reducing the computation cost. For example, the beam is not bending and effective particle are rain, snow, and gravel. The cloud and cloud ice is ignored. Cloud ice are ignored. This is analysis increment after assimilation of GPM-DPR. This figure is a traditional for dBAR, and this figure shows the result of the hybrid for dBAR. So in the hybrid for dBAR, the increment is widely spread than the traditional for dBAR. This figure shows difference of forecast from traditional DA and hybrid DA. The blue color shows the dry area, and red color is the wet area. And this is a result of the precipitation forecast. The read time is 9 hours. In the traditional data simulations, the forecast is overestimated here. Precipitation forecast is overestimated here. So in the hybrid data, using the hybrid data simulation, its precipitation forecast is improved. And this is a fraction scale score. In this case, the x-axis is spatial scale and y-axis is FSS. And this figure shows y-axis is test minus control. So you can see heavy rain rate, and these colors is improved. However, the weak rain is underestimated on large scale. And the reasons why they underestimated is the weak rain bias is changed to worse. So forecast rain is reducing to provided the heavy rain because heavy rain. Sorry, this is a summary, and I have been developing of hybrid for by using tangent linear and adjoint of cloud microphysics scheme. The bias of cloud forecast is successfully reduced. The tangent linear grows the perturbation smoothly in almost process. The adjoint model propagates the gradient with respect to hydro meteors, and the benefit of flow-dependent DA is for list. And the future work is updating the observational data and more case studies testing severe weather events. And it is important statistical verification. We will do statistical verification of long terms. Thank you.